Jessica, are you there?
Yeah, I'm here.
Oh, okay.
Can you see my slides?
Yes, I can see it.
Okay.
Okay. I saw people still coming, but let's get started. Hello, everyone. My name is Jin Lu, the co-chair of Dashu Virtual Journal Club. So let's give a brief introduction of Dashu. Dashu is a 501c3 nonprofit organization. So we have the tax exempt status by federal and by California state. We have many strategic partners, including SFASA, BAES, CABS, and so on. We are a young organization founded about like 3 years ago. The good news is our membership is free. As long as you attend any of our event, you will automatically be a member. Our administrative cost is very low of our work as volunteers. So if you are interested in funding us, all the funding goes to serve the community. The goal of this organization is to provide a virtual community for people interested in data science, and we can help each other in the community. And currently we organize like an international scientific conference, mostly journal club, technical seminars, career development events, and educational lectures such as legal service, legal series. Currently, we are actively seeking members, volunteers, and new ideas. Could you go to the next slide? Yeah, we have a great event coming for December. SFASA 19th anniversary celebration and a career development panel discussion. And Dashu is a co-sponsor for this fabulous event. We have two prestigious names in our speaker list. Everyone knows their names. Professor Efron, who developed many hugely influential statistical methods, including Bootstrap. Professor Efron will accept the international prize in statistics which is considered as the Nobel Prize in the field of statistics. Also, Professor Michael Jordan, he is reported as the world's most influential computer scientist. And we also have many fabulous names in the panelist too. And if you are interested in and you want to come to our event, you can Google SFASA to find more information about this activity. And next slide. A little bit more about the Virtual Journal Club. So currently we do it monthly. If you go to our website, you can see a blue Virtual Journal Club logo, and you can click on it. You will find all of our previous journal clubs. We usually share slides and the recordings if the speaker give us the permission to do that. Currently, we have about 10 journal clubs on the website. For journal club, we need your help in many ways. If you are interested in hearing particular topics, you can let us know. If you are working on some data science topic and want to present, you can also let us know. If you like our journal club, and you can help us to spread the word and broadcasting our activities and events. Yes, that's how you can help us. Next slide. Yeah, I'm very honored to introduce today's speaker and topic. Dr. Jessica Lee is our Dashu's old friend. He's currently an assistant professor in the department. In the Department of Human Genetics at UCLA. She graduated from University of California, Berkeley. In her young and promising career, she has already published more than 30 manuscripts in leading journals, including Science, Nature, Cells, Genome Research, PNAS, just naming a few. She has also achieved many awards, including highly competitive Alfred P. Sloan Research Fellowship, Johnson Johnson Women in STEAM 2D Math Scholar Award. Could you please mute yourself? Yeah, miss. Also, Hillman Fellowship and Pharma Foundation Research Starter Grant in Informatics. Recently, she has also won the ICSA Junior Research Paper Award. Today's topic is about the Neyman-Pearson classification algorithm and NP receiver operating characteristics. The topic is about recent publication of Science Advance. So this work is to address one commonly faced problem in machine learning or statistics. For like a classification task, we usually want the type 1 error less than a certain threshold. However, in practice, it's very hard to satisfy the type 1 error control objective. So without any further ado, I will give the floor to Professor Lee to talk about her fascinating research.
Thank you very much, Jane, for introducing me, and it's my great pleasure to be back again to present my research at the Dashu webinar. Last time we talked about our method for single-cell RNA-seq data, and this is a very different topic. But I think this also has a lot of applications in biomedical sciences as a general framework. And I'm Jessica Lee, I'm from UCLA, and this is my joint work with Dr. Xin Tong, who is an assistant professor at University of Southern California, Dr. Yang Feng, who is an associate professor at Columbia University, and my student Yiling at UCLA. So first of all, I want to introduce some basic notations I will use throughout this talk. First, we define the features as p-dimensional vectors, which represent, for example, health characteristics of a person, and class labels, which are binary. In biomedical sciences, this can represent a disease status of a person. So for binary classification, our goal is to construct a data-dependent classifier, which is a binary function that maps from the feature space, the p-dimensional feature space, to the binary space. In order to do that, we need training data. And here we just denote the training data sample size as n. And for convenience, people often assume the training data points are IID. A classification method is something I want to clarify and distinguish from classifier. We refer to a classification method as a way to construct a classifier H from training data. For example, logistic regression, support vector machines, or random forest are all classification methods. So with a classification method and with a training data set, then we can build a classifier H. Because we regard the training data as a random sample, therefore, the resulting classifier H is also random. How do we evaluate a classifier? So we use some metrics called classification errors. Here we denote X and Y as another pair of random variable, independent and identically distributed as our training data. So we assume they come from the same population. Then the classification error, or we call the risk, is actually the probability that on this independent random variable pair, the predicted label HX is different from the actual label Y. So by decomposing this probability into a sum of product of marginal and conditional probabilities, we can further represent this risk as a weighted sum of the type 1 error, which is R0H, and the type 2 error, which is R1H. So here you may see that I use different colors to represent probabilities. The reason is that here those probabilities have different meanings. The first one, the purple one, actually is the probability with respect to the joint distribution of X and Y. The blue probabilities are with respect to the marginal distribution of Y, while the orange one and the red one are with respect to the conditional distribution of X given Y equals 0 or Y equals 1. And here when I write out the risk, RH, the type 1 error, R0H, or the type 2 error, R1H, I'm actually conditional on H. In other words, I'm conditioning on the training data. So therefore, if we condition on the training data, H becomes fixed, and all the probabilities RH, R0H, and R1H becomes constants. However, if we consider the classifier H as random, then all the three quantities or metrics become random. This is very important because I will use this nature in later slides. So first of all, before I introduce our Neyman-Pearson paradigm, I want to define what do we call as the classical paradigm. So we call classical paradigm as this classical goal. That is, we want to find a classifier to minimize the risk. So this is how we define a classical oracle classifier, because this is the best we can do. However, because the risk itself is not observable, we have to observe the population in order to observe the risk. In practice, we don't observe the population. So therefore, the classical oracle classifier is a gold standard, but we can never achieve it. Another way to formulate the classical oracle classifier is to use the regression function to define it. Here, eta x is the probability of y equals 1 given x equals small x. So this eta x is what we call the regression function. So our theory told us that if we just put an indicator function as a cutoff, say if the eta x is greater than 1/2, we predict 1, otherwise we predict 0. This is exactly the classical oracle classifier, and its another name is Bayes classifier. So other things are in classical classification theory, and here we call them as the classical paradigm. In practice, since we don't observe the oracle, how do we construct a classifier? There are two approaches. The first approach is to directly plug in the empirical risk instead of using the true risk, the population risk. And then this becomes an optimization problem. As long as we can find a minimizer of the empirical risk, R hat, then we find a classifier. Another approach is based on the Bayes classifier. Our idea is that since eta x, the regression function, if we go back, you can see it's the probability of y equals 1 given x equals x, also depends on the population. It's not observable. How about we just plug in eta hat x to replace eta x, and then we get a classifier. So this is what we call as the plugging approach. Both approaches are existing in the current machine learning or statistical learning literature for classification, for binary classification. However, sometimes in many applications, we need asymmetric error control, which cannot be satisfied by the current approach. If we look at this decomposition again, the risk is a weighted sum of the type 1 error and the type 2 error. And their weights are defined by the marginal probabilities of y equals 0 or y equals 1. That means it depends on the population level proportion of the labels that belong to 0 or the labels belong to 1. And these weights are fixed. However, in practice, we see that type 1 error, R0H, may be much more important than the type 2 error, R1H. For example, in cancer diagnosis, let's say that if we think a tumor sample as class 0, a normal sample as class 1, then the consequence of mispredicting a tumor sample as normal will lead to life loss, which is unacceptable. On the other hand, if you mispredict a normal tissue, class 1, as malignant, class 0, although this is also not good because it will increase patient anxiety and additional medical costs. However, the consequence is not comparable to the other way around. So in this case, the type 1 error is much more important than type 2 error. And we need a way to control the type 1 error. And we call this as asymmetric error control. Before I go into the detail about how to do that, let me further clarify some notations. So like I said, we have training data denoted as x1, y1 to xn, yn. We also have a separate test data in evaluating our classifier. We call them, we refer to this as samples at n, and we add a prime notation. So to evaluate a classifier constructed from training data, here we denote that by h hat. We have 3 risks. The population risk, which depends on the true joint distribution of xy. We also have empirical risk, which we can calculate based on our training data, because the true risk, the population risk, is not observable. We can also evaluate the empirical risk on the test data. So here to differentiate those 3 notations, we use R for population risk, R hat for empirical training risk, and R tilde for empirical test risk. Similarly, we introduced the notations for type 1 error, 3 versions, and type 2 error, 3 versions. So just make a distinction that type 1 error actually has R0, type 2 error actually have R1 to reduce your confusion. All right, so you may wonder, why do we care about the population error? Why isn't the empirical errors based on training data or test data good enough? This is a cartoon example we posted on YouTube. If you're interested, you can check out the link after we post the slides and watch our video. So here the setting is that assume we are looking at all the people in the world, and this is our population. So the color here indicates some diagnostic metric. So more red means that this person is more likely to be diseased, and more blue means that this person is more likely to be healthy. And the plus indicates this person actually has the disease. And minus sign indicates this person doesn't have the disease. So we can consider this color as a one-dimensional feature for us to make a decision. And the plus and minus signs are the labels, are the binary labels. So the question we want to ask is, if we are a doctor, where should we set a threshold so that the false negative rate on this population can be controlled under 1%, while the false positive rate is minimized. So this means that as long as we are under 1%, we want to get to 1% as close as possible so we can minimize the false positive rate, because the false negative rate and the false positive rate have a trade-off. One is larger, the other is smaller. So you can see here, I simplify the problem by saying, how about I have 5 thresholds, and let's pick one to satisfy that the false negative rate is under 1% and the false positive rate is minimized. Where do I set the threshold? Let's say if I observe the whole population, it's not difficult at all because I can just count. I can just find the threshold by looking at all the people here, and so the false negative rate is exactly 1%. However, the population is not observable. So the oracle one is threshold 4. Assume I have the population. So this, I know this should be 4. But since I don't observe the population, what I observe is actually a random sample from the population. For example, only those people. Then where should I set the threshold? The most intuitive way is to set a threshold on this sample so that the observed empirical false negative rate is 1%. And this will give us threshold 2. But on the whole population, this threshold will correspond to false negative rate 7% instead of 1%. So if we observe more and more random samples every time, we will find the threshold. So if we collect their results, we actually get a distribution of the thresholds. And from this result, we can see that for about half of the chance, we would actually pick a threshold which is actually worse than the oracle one. So that means threshold 1, 2, and 3. So if we choose any of those, then the actual false negative rate you would achieve on a population greater than 1%. So this becomes an issue because based on your random sample, you cannot actually achieve the desirable false negative rate control. So this gives us a motivation to control the population false negative rate instead of the empirical false negative rate. So translate back to our binary classification setting. We can also think about the type 1 error as the thing we want to control. And if we really want to control the population type 1 error instead of the empirical type 1 error, what do we do? Here is our formulation. In our statistical formulation, there are 2 key parameters. The first parameter is the upper bound or the threshold we want to set on our population type 1 error. Here we denote this by alpha in blue. Another parameter is the delta in orange, which we call as the violation rate. So our goal is that we want to control the population error of a classifier H hat under alpha with probability at least 1 minus delta. Why do we need the delta? The reason is that H hat is random because our training data is random. So therefore, as a random quantity, we have to consider the probability that it's under alpha because we cannot say that with probability 1, this quantity is under alpha. That is not possible for a random population type 1 error. Because H hat is random, then the population type 1 error is random. So therefore, what we can do is to control that its probability of exceeding alpha is small. And we set an upper bound on that small violation, which is delta. So this is our formulation. And before our formulation, there are some existing work in the field, especially in the engineering field. There's a famous topic called cost-sensitive learning. Many people heard of it. And the idea here is that it directly modifies the objective function in empirical risk minimization. That is, the weights of the type 1 and type 2 errors are not the probabilities of y equals 0 or y equals 1, but some arbitrary costs. So you can make the weight of the type 1 error really large in your objective function. So when you minimize your modified objective function, the resulting type 1 error can be very small. However, there are some issues for applying the cost-sensitive learning to biomedical sciences, especially disease diagnosis, because it's not clear how we can assign the costs. Can you say that a false negative rate is 100 more times more important than the type 2 error? It seems not natural. And also, even if you assign the weight as 100 over 1, you still cannot know what will be the type 1 error you could achieve at the population level. So therefore, if the population type 1 error upper bound alpha here is a more natural control, then the cost-sensitive learning does not provide a direct solution. Another approach that's very widely used, that's also something that first came to my mind when I heard about this problem, is to use the receiver operating characteristics, the ROC curves, which looks like this. This is from Wikipedia, so a ROC space. So there are many labels of the two axes, just corresponding to the terminology we use here. We refer to the x-axis as type 1 error, y-axis as 1 minus type 2 error. If we're closer to the upper left corner, we're doing better. So this seems very natural, right? We can just look at the whole ROC curve and find the threshold to satisfy our type 1 error control. However, the problem is that because we never observe our population type 1 or type 2 errors, we only observe empirical type 1 or type 2 errors based on training data or based on test data. So therefore, the ROC curves we plot here in practice are those empirical type 1, type 2 errors. And based on this ROC curve, there's no direct way to say, okay, I cut here, then my population type 1 error will be controlled under alpha with high probability. And I'll show a toy example to demonstrate that. So in this toy example, we have a one-dimensional feature, the simplest case, and the two class conditional distributions that is given y equals 0 or y equals 1. The distribution of x is just two Gaussian with different means. And the two classes have the same probabilities 1/2. In this case, a classifier would simply be setting a threshold on this one-dimensional feature. The reason we chose this toy example is because we can easily compute the type 1 and type 2 errors based on the CDF of Gaussian distribution, of standard Gaussian distribution, which is just give us a nice closed form solution. So we know the population type 1 error has this form, the population type 2 error has this form. What we do is that we simulate from this distribution a training sample with size 1,000, and we repeat this simulation for 1,000 times. We also separately, independently simulate test sample with size 1,000, and we did 1,000 simulations. So we have 1,000 training test sample pairs. So what we do is that by varying the threshold t in this classifier, we can actually use the test data to plot the empirical type 1 and 1 minus empirical type 2 errors. So we get an ROC curve. Let's say that our alpha, the upper bound we want to put on our population type 1 error is 5%. Where do we find the threshold from this ROC curve? The most intuitive way is just to find the vertical line at empirical type 1 error 0.05, and then find the threshold that's to the left of it but closest to it. So we get the threshold based on the first simulation. Second simulation, we get another classifier, another threshold, and 1,000 simulation, we get another threshold. So putting those 1,000 thresholds together, we get 1,000 classifiers. And if we evaluate if we look at the distribution of their empirical test type 1 error, as expected, they're all under 5% because that's how we pick the threshold. But if we look at their population type 1 error, based on our closed form formula, you can see that a large proportion of them are actually larger than 5%. So this example shows that if you directly just pick a threshold from ROC, from the empirical ROC, you would not achieve a control on the population type 1 error. Another common use of ROC is to compare two classification methods. For example, logistic regression and random forest. So here, if we want to say which one's better, you can see in this example, it really depends on where is the type 1 error you are concerning about. Let's say that if you really care about a small type 1 error, then probably random forest is slightly better. But if you care about large type 1 error, logistic regression looks better. However, from this plot, you cannot directly associate your population type 1 error upper bound alpha to the empirical values here plotted in this curve. So the message is that the empirical ROC space provides no direct information on the population type 1 error control. Then we need something new. And this is our Neyman-Pearson classification. This is the formal definition of the Neyman-Pearson paradigm. So on the population level, the objective is to minimize the population type 2 error with the population type 1 error under alpha, say 5%. And the first idea of the Neyman-Pearson classification paradigm came from the engineering community in 2002. But at that time, what they tried to control the type 1 error is alpha plus some epsilon, a relaxed version of this one, not exact version of this one. Until my collaborator, Dr. Tong at University of Southern California, when he was doing his PhD with Dr. Philip Regulet at Princeton, so they reformulated this problem to say that we actually need an exact control of the population type 1 error. So they define some theoretical properties, including the NP-ROC inequalities, to define what is an NP-ROC classifier and how to construct it using the plug-in approach. So these are very great theoretical work. But at that stage, the work is not directly applicable to practice, because in the plug-in approach, the key challenge is that we need to estimate the conditional densities of the x given y equals 0 or y equals 1. And this is very challenging when x is multidimensional, if it's greater than 3. And that's what we have in practice. So therefore, the key challenge we were facing when we started this collaboration is to think about a way to actually make this Neyman-Pearson paradigm work with existing state-of-the-art machine learning binary classification methods. So just as a comparison to better illustrate the difference between the classical paradigm and the Neyman-Pearson paradigm at the oracle level, at the population level. The classical paradigm seeks an oracle classifier to minimize the population risk, while the Neyman-Pearson paradigm seeks a classifier to minimize the population type 2 error with population type 1 error under alpha. And alpha as a threshold reflects users' conservative attitude towards the type 1 error. This name has a close connection with hypothesis testing, the Neyman-Pearson lemma. If we recall this in some of our classical textbooks of mathematical statistics, this is the Neyman-Pearson lemma. So the connection is very straightforward. In the Neyman-Pearson lemma, we're tackling a testing problem. So it's by nature asymmetrical, because our default is the null hypothesis, and we want to reject it or not reject it. So in order to find the rejection region, our idea is to first have a significance level alpha fixed. So that is basically the upper bound on type 1 error. And the goal is to find a decision rule such that the power is maximized. And the power is 1 minus the type 2 error. So maximizing the power is equivalent to minimizing the type 2 error. So although here the type 1, type 2 errors are defined in the testing setting, not in our classification setting, but you can see they share similar flavor. Neyman-Pearson lemma is so fundamental that it gives us a good reason to use likelihood ratio test as the most uniform and most powerful test for doing statistical tests. And so this gives our idea to actually use the plug-in approach to construct density ratios for achieving the NP paradigm. So that's the connection, and this is where the name came from. But as I said, estimating density is in itself very difficult. So that's why we need something different. And this is what we published in our Science Advances article about our NP umbrella algorithm. So this algorithm is, for the first time, allows us to connect the NP paradigm to practice. So specifically, what we focus on is the scoring type of classifiers. For example, logistic regression. What do we call as a classifier as scoring type? So this is for the classification methods. If you train them on a training data set, then you will actually get some scoring function based on which you can set a threshold to achieve a classifier. For example, in logistic regression, after you fit
the model to your training data, you will actually have an estimate of this regression function. That is the p hat y equals 1 given x. And this is what we call the scoring function, because based on this, you can see the threshold. In the classical paradigm, the threshold is by nature 1/2, because this is 1/2 is from the Bayes classifier. So if you have this estimated posterior probability larger than 1/2, you predict 1. Otherwise, you predict 0. But in our NP setting, we need to change this threshold because we have an alpha to achieve. So we just generalize this scoring type of classifier to this form. It's an indicator function that depends on a scoring function trained from training data and the threshold. So with those components, you have a classifier. So as I said, under the classical paradigm, you only need to estimate F. And you only need to construct F from training data. Under the NP paradigm, you need to construct both F and T from the training data given your alpha and your delta. Alpha is type 1 error upper bound, delta is the violation rate. So we just showed this formulation again. In order to achieve this, that is the type 1 error violation probability is under delta. How do we do it? Our algorithm actually makes use of the order statistic to achieve this. And our idea is based on sample splitting. We split our training data into 2 parts. One part is a mix of class 0 and class 1 samples. Based on this, we train a base algorithm and we obtain a train scoring function, which is our F. And we have a left out class 0 sample for which we will use to find the threshold T. So what we do is that we just apply the train scoring function to this left out class 0 sample, and we will obtain a set of classification scores. On those scores, we will find a threshold so that the smallest threshold that achieves the violation rate under delta would be the one we pick. Why do we want to find the smallest threshold? The reason is that if we go to a higher threshold, we will put less class 0 as class 1. So we will have a smaller type 1 error for sure. But meanwhile, we will have a larger type 2 error. So having the smallest threshold to achieve the violation rate under delta will guarantee that given this scoring type method, say logistic regression, we are doing the best we can. We are finding the threshold that achieves the type 1 error control while having the smallest type 2 error, given this sample splitting also. So the order statistic is the key trick or the key technique we here to achieve this. And it's based on this lemma. So this lemma is a result, a classical result for order statistic distribution. Let's say we have an IID random variable and the kth order statistic is tk. So then we can derive its right tail probability in this combinatoric formula. So you see on the right-hand side, it depends on the CDF of each random variable, is this form. And the trick here is that if we replace this threshold T right here by F inverse 1 minus alpha. So if we just replace this in our lemma 1, so the right-hand side T will be replaced by that too. So we actually cancel out the F on our right-hand side. So now you see the upper bound here becomes no longer relevant to the CDF, which is something very important for our results, because this upper bound is exactly the upper bound we have in our main theoretical result right here. This is what we call the population. So what we do is that we apply a train scoring function to the left out class 0 sample, which we denote as size n. So after we apply that, we will have n classification scores, T1 to Tn. Here, they are just one-dimensional, real valued. And then we denote Tk as the kth order statistics. Then for a new observation, let's say for the new observation, we want to make prediction. And we apply the train scoring function. So we can get a classification score for this new observation. We call this T. So then in this case, because if this new observation is, we say it's from class 0, then T and my T1 to Tn would be IID. So you see that the thing is that based on this T, I actually obtain a classifier that is let's say if I choose TK as my threshold, the kth order as my threshold, then the classifier is just the indicator that my classification score on the new observation is larger than TK. That's a classifier. And then its population type 1 error R0 can be written out in this way. So here in this type 1 error, the probabilities with respect to the T, the new observation, is not with respect to my training data. So the training data and the threshold is actually conditional here. So basically put TK in the conditional. So the F is just the CDF of the class 0 score for T, if T is from the class 0. So we use that as the CDF. And that's my type 1 error. So you see that as it's still random because here the randomness is from my training data, since the order statistic TK is random. So therefore, if we want to control its type 1 error violation, we just put the type 1 error larger than alpha and compute this probability. If we really do that, we have 1 minus FTK larger than alpha. And if we rewrite it, we actually achieve what we have under lemma 2. So we have the upper bound. So the nice thing here is that the upper bound we derived based on order statistic only depends on 3 things. First, the left out sample size n. Second, the alpha type 1 error upper bound. And third, the threshold k. So the k is the order. So let's say that if we really want to control this violation rate under delta, what we can easily do is that we just try to find the k order that will make this upper bound controlled under delta. Another thing I want to say in this remark 1 is that this inequality here, less or equal than, is actually tied, is actually equal if the F, the CDF is continuous. That means if your score classification scores are continuous, and this holds for many classification methods. So this is how we search for the order threshold. That is, we just compute this upper bound, which we denote as VK, use the notation. If the VK is less or equal than delta, for among all those Ks, we find the minimum, the smallest threshold as our threshold. And another nice thing we can learn from this result is that we can actually derive the minimum sample size to leave out from our class 0 to guarantee this control. Because if we solve this, we can show that if the n is the largest possible order, at least we want to make that satisfy Vn less or equal than delta. Because if we don't have that, then all the orders will fail. So if we can reversely solve Vn less or equal than delta, we can obtain that n is must be greater or equal than this ratio, log delta over log 1 minus alpha. But the good thing is that this n is not very large if you set delta to be 0.5, alpha to be 0.5. It's like in the hundreds. So this left out sample size also works for many cases where we have big data. Okay, so just to summarize the algorithm, because that I just briefly talk about the foundation for our algorithm. This is the actual algorithm. So our input is a training data, which is a mixed IID sample of class 0 and class 1. And alpha is our type 1 error upper bound. Delta is a small tolerance level for violation rate. N is the number of random splits. Because if you recall, we rely on sample splitting. And every splitting will give us a different NP classifier. So that's why we want to do an ensemble to make our classifier have a more stable type 2 error. So that's the idea. So that's why we can allow multiple random splits and then do ensemble in the end. And this function, rank threshold, is based on our proposition. So essentially, you input n, alpha, delta, those 3 things. So you just compute this VK, the violation rate upper bound, for each possible order from 1 to n. So you just compute them, and then you use this VK less than or equal than delta to find the smallest k that satisfies this inequality, and that's the k star, and k star will be returned. So you can see the nice thing here is that we don't even need the training data to find k star, because k star is just determined by n, alpha, and delta. So we just keep this K star with this using this function. And then using our data, this is our procedure, NP classifier. First, we randomly split our class 0 into 2 halves. So we denote half of the class 0 size as n, and we use that rank threshold function given n, given this n, given alpha, given delta to return a K star. For each of the random splits, so for I go from 1 to m, we randomly split class 0 into 2 halves. We pair one half with the class 1 data as our mixed sample, and the left out is denoted as x1 to xn. So for the mixed part, we train a classification algorithm such as logistic regression, and we obtain a score function. Then we apply the score function to this left out data, so we obtain fi x1 to fi xn. And those scores, we denote them as our ti1 to tim. So we sort those scores from the smallest to largest. After the sorting, we apply the K star, find by the rank threshold function to obtain the threshold. So then you can see we have everything we need. We have a scoring function, we have a threshold, so we have an NP classifier. And in the last step, if we do multiple random splits, we just do an ensemble of those NP classifier by majority voting. So this is our algorithm. It's very simple to implement, and also you can see it's adaptive to all scoring type classification algorithms over here. So how does it work in practice? Let's look at the toy example again. So now I'm using the same setting, but I'm not going to intuitively pick threshold from each data set just based on empirical type 1 error. I'm going to use this algorithm to pick a threshold. And this is what we do on empirical type 1 error. This is not our target at all, but it's just good to show how well it's doing. So because we target on population type 1 error. So as a result, the empirical type 1 error is also not that large. But the population type 1 error, if we look at the true target of our paradigm, you can see we did manage to control population type 1 error under alpha 0.05 with high probability, which we want to, actually our delta is 5% and here is only 4.1%. So we actually achieved that. So we did control the population type 1 error. But we're not done yet. So with this algorithm, we are able to construct NP classifier. But how do we use a graphical tool to compare different NP classifiers? That's still a remaining question. We know the empirical ROC space is not compatible with our paradigm because it's x-axis and y-axis are based on empirical type 1, type 2 errors, right? So we need something new. So motivated by this, we developed a new graphical tool called NP-ROC, which allows us to plot alpha of various alpha thresholds from 0 to 1 on the x-axis, and y would be 1 minus type 2 error. So here I have to clarify that what we mean by type 2 error is not exactly the population type 2 error, but it's some conditional population type 2 error, which means that we are conditional on the training data, but other than that, it's still the true probability part. So this is how we define as the NPC band. That is, we have a high probability type 1 error control achieved by our algorithm. How about type 2 error? We want to say something about it. In order to do that, we use the same idea to leave out some class 1 sample for us to evaluate the population type 2 error, the conditional population type 2 error. So we revise the sample split. Now we split our sample into 3 parts. A part for training, the same. A part for finding a threshold, the same. And the third part, left out class 1 sample, is to find some upper and lower bounds on some conditional population type 2 error. And the intuition here is that we need to pay a price to know how well we will do in the future. So the price we pay is that we leave out some class 0 sample, so we have fewer sample for training. But the idea here is, if you have a predefined alpha, then you should use what we give in the algorithm, because that will give you the NP classifier. You have more data for training. But if you want to compare two different methods, say logistic regression and random forest, and you are not very sure the alpha value to pick, then the NP-ROC band will give you some data-driven guidance. So this is what we get. So for every alpha in the x-axis, we will find a lower bound and the upper bound for this 1 minus type 2 error, and we connect them as a vertical line. And we extrapolate them by actually using the step functions to connect those vertical lines into an NP-ROC band. So the advantage of doing this is that we will actually be able to compare two classification methods. For example, in this example, we are doing linear discriminant analysis, short as LDA, and we have two one-dimensional features. Let's say if the question is, which feature is a better feature for building a classifier, if we only want to pick one feature. So here the red band corresponds to the classifier with varying alpha based on the second feature only. And the black band uses the first feature only. And in this example, we can see that the two features have relative advantages that change with alpha. So for small alpha, second feature is doing better. For large alpha, the first feature is doing better. Comparing the two NP-ROC bands, we can roughly see, oh, if my alpha falls here, I should pick feature 2. If my alpha falls here, I should pick feature 1. So this gives us some useful tool. And also, looking at the 1 minus type 2 error, we can also evaluate whether our predefined alpha is actually achievable in our data. For example, if I really want to have alpha equals 5%, let's say I use the first feature, and 5% is right here. You can see this is too low for me. So I don't think this is acceptable. So therefore, I may think, oh, my alpha cannot be too small. I can only afford a larger alpha. So I may go here. I may pick alpha equals 0.2. So this NP-ROC band will provide some practical guidance for choosing a reasonable type of error upper bound given the data. So finally, in our ongoing work, we're doing some feature ranking under the NP paradigm. So the motivation is that if in a disease diagnosis problem, we do have a clear alpha in our mind, so which means we do not care about the overall performance of a classification method, but we only care about the performance under a specific alpha. Then the important features may be different from the case where you care about the overall AUC or you care about the risk. That's the classical paradigm. So in this case, how do we rank our features? Or in general, more general, how do we do model selection? If I have multiple classification models, which one should I pick under the NP paradigm? And this is our ongoing work, and hopefully we will release our archive version very soon. So to summarize, I first introduced the binary classification, the notations, and our formulation. And the key question in this part is, where is the randomness? There are so many randomnesses. There's a randomness in the training data. There's also randomness on a new observation. So we have to entangle those randomness. And the second part is I introduced our NP classification. I introduced the formulation. That is, we want to control the type of error under alpha with high probability. I then introduced our NP umbrella algorithm to connect this formulation to machine learning algorithms. And the third part is about the graphical tool, which I only briefly introduced for comparing two classification methods and also how to choose alpha adaptively. So since I still have some time, I will say about our paper. So this is our paper, which was published in February this year in Science Advances, which is a new multidisciplinary journal under AAS, and our R package NP-ROC on CRAM. So up to now, I didn't check the most recent statistics, but like at least last month, the download has been more than 8,000 times, which is which we are very happy about. And you can email me if you have any questions about our work. So lastly, I want to just show a quick example about how to use our R package. So you can just call it after you install it, And in this simple simulation, we simulate two-dimensional features using a logistic regression model. And this is how the data looks like. So if we directly use the R function GLM to fit logistic regression and the type 1 error, here I'm just using test type 1 error, not actually the population type 1 error. So the test empirical type 1 error, you can see the distribution is pretty large if we repeat this for 1,000 times. But with our NP-ROC package, you can call the NPC function, specify the method as logistic, alpha 0.5. The default for delta is also 0.05. And you can see that now the type 1 errors you get on test data are also much smaller than what you use the GLM function for. So finally, I want to thank my two collaborators, Xin and Yang at USC and Columbia, for their important contribution on our insightful discussion throughout this whole project. And also, I want to thank my student, Eileen, for the ongoing work, although I didn't have time to talk about. And also, I want to thank my funding agencies for their support. Thank you.
Okay, thanks, Dr. Lee, for the very informative and inspiring talk. So yeah, if anyone has any questions, you can put on the chat box, or you can just unmute yourself and speak out. Any questions? Yeah, I think I have one question. Could you go to the slide 33?
33, sure.
Yeah.
Okay, yes.
So for the output, it's an ensemble model, but not a single model, right?
But you can set m equals 1. So for even if you just do one random split, you can still achieve the type 1 error control. That's not a problem.
Oh, okay.
Yeah, the example is just to make the type 2 error. Actually, we just want to make the type 2 error have a smaller variance.
Oh, okay.
Yeah.
Okay. Cool. Yeah, I have another one. And so how about so how do you decide like the split or ratio on class 0? What if the class 0 is a real class?
That's a very good question, and it's a very important question, because in many applications, the class 0, which is the more important class, is actually rare. So for example, if we do disease diagnosis, we may have much fewer patient sample than data from normal people. So that's the problem we are actually considering as an ongoing work. And actually my two collaborators, Dr. Xintong and Yang Feng, they have done some interesting analysis on trying to find the split ratio in a data adaptive way. So, but that thing is still ongoing, and we hope to be able to talk about that in some time soon.
Okay.
Yeah.
Okay, thank you.
Thank you.
So for the R package, it only support a few existing machine learning models, right?
I think we now support 7 or 8 methods, including logistic regression, support vector machine, random forest, AdaBoost, and also LDA. So at least those major things are supported. And I think neural network can also be supported as well without problem.
Okay, so does the user need to implement the procedures to if they have a new?
Oh yeah, that's a very good question. If users have a new method, if users have a new method, then the idea is that you could actually follow this procedure to obtain a scoring function, and then you can actually let our algorithm find the threshold for you.
Okay.
So basically, if the classification training part is different, then you have to specify the classification scores for us.
Okay, yeah.
then you can consider the classification score as a one-dimensional reduction of the features. You just reduce the feature from p dimensions to one dimension.
Yeah. That's true. So when people do like the tuning of a hyperparameter, it should all be done within the classification algorithm part.
That's right.
Okay.
Yeah. But this is also a very good question. It's also our ongoing work. So we are also considering incorporating this NP paradigm, this asymmetry idea into the training phase. So the trained scoring function can work better for our purpose. So that means the type 2 error could be smaller, but this is still something ongoing.
Yeah. That's why. Yeah. Thank you.
Thank you.
Oh, yeah, there's a question in the chat box.
Okay, let me see, because I have to leave the full screen to see Zoom. Chat box, okay. It seems the sample size n is for class 0, but not class 1. Do we need another formula to calculate sample size for class 1? What is the total sample size needed? That's a very good question. And actually, I have to say this is also our ongoing work, because I know for biostatisticians, the sample size calculation is very important. So the idea is that in order to compute sample size for class 1, we will use type 2 error. Because here the sample size for class 0 is only for the consideration of controlling type 1 error under alpha with high probability. So if we want to have some type 2 error control, then we would say, okay, if we don't have class 1 of this much, we cannot control type 2 error of this much. But still, that's our ongoing question. And hopefully we can publish this soon.
Yeah, I have another question because in practice, especially for diagnosis, when we have like a multi-class scenario, can this Neyman-Pearson paradigm be extended to multi-class scenario?
Yeah, we are currently working on the multi-class scenario. Yeah.
Oh, cool.
Yeah, this is a very good and very important in practice as well.
Yeah. Yeah, and you also talk about the NP-ROC, the band for NP-ROC. So if a practitioner who do not have like a pre-specified alpha in mind, so can they like still use the Neyman-Pearson paradigm?
Yeah, they can still use the NP-ROC band, because the NP-ROC band just plot all the alpha values between 0 and 1, so give you the whole range. And so in that case, you could look at the whole band and decide, oh, maybe this alpha is reasonable to me.
Yeah.
And then you can go back to the algorithm to run the algorithm with that alpha.
Okay, cool. Yeah, if the audience has no more questions, yeah, if you have more questions, you can like send Dr. Lee email. And if you have any question for our event, you can also send the email to us. I think this is for today. It's already 10 a.m. So yeah, thanks everyone, and thanks Dr. Lee for her fabulous talk.
Thank you, Jing, and thanks all the audience.
Yeah, thank you.
Thank you. Bye.
Bye.
Bye.